Hello, welcome. My name is Brandon Eugene, and today we are going to be learning about linear and nonlinear regressions. We're going to be doing this through a model representation of the Anton equation. Let's get started. We're going to be doing this completely through coding in Google Colaboratory. So first, let's go ahead and get our data. All right. We're going to find our data in GitHub. And what we need to do is we need to be able to import this data, WGET. And what we're going to do next is we're going to go straight to the site and copy the URL right into our code. But we don't need all of this. We just need our raw data. Get this out of here for you. And we're going to hit Control V and then Shift Enter. Now that will give us the file that we just received from the GitHub site. As you notice, it is called water vapor pressure.csv. So what we're going to do next is we are going to import Python, which is going to be our code collaborator on our coding today. Python's a great interface for what we were about to do. Import numpy as np. Shift Enter. Next, we're going to want to load up our data. So to even get started with that, we need to hit data equals np.load text, and the name of our text is water vapor pressure.csv. And now back in our data, the way they use to separate each variable, all our variables, are through commas. So our delimiter in here is going to be commas as well. Forgot my comma. That's funny. All right, now let's look at our data, okay? We know our file is right here, but we can also put all of that raw data that we have from right here right into our code. All right, let me just make sure we can see everything here. Perfect. Just want to make sure. Now before we start here, what we're going to do next is we're going to label our variables. Our X variable is going to be this first column, and our Y variable is going to be the second column. X is the independent variable T, so T is measured in kelvins in this data, and temperature. T is temperature measured in kelvins. And the way indexing works, our column 1 is number 0. And that means our log P of our data is also going to be one. Now Python doesn't understand log P immediately, so in order for this to be graphable data, we're going to have to actually put in this equals mp.log10, and then for all of our data so that it can fit on the graph, or we'll have a very wacky graph. Trust me on this. What we're going to do next is actually implement our graph and put it in right into our code. So we're going to use a software called Plotly. So from plotly.subplots, import make underscore subplots. And then import plotly.io as PO. We like that. Now to the nitty-gritty to actually making our graph. All right, so first what we're going to need to do is we're going to hit fig equals make underscore subplot, which we just grabbed that data over so we can even be able to do this. We're going to have our data has one row, rows equal 1 and columns equal 1. Perfect. And now next, to actually make that a graphical with data, fig dot add underscore our scattered plot, where our independent variable x is going to equal T temperature measured in kelvins. Our y is going to be our log P. Next, our mode of our graph is going to be markers, because we just want dots. And then our name, we're getting all this from our data we've already implemented. All right, now here's our graph. Now let's just make sure we know what this is correct. We have water vapor pressure. So water vapor pressure, boiling point of water is about 373 kelvins. So if we go to our graph at 373 and we go up, we get about the atmospheric pressure, because at the atmospheric pressure, that is the boiling point of water, which is about 10 to the fifth. And we have it in logs, so 10 to the fifth would make it 100,000 pascals. And that kind of aligns with our data. So we know that at the very least, the information that we got from our GitHub site is accurate. Now, what we're going to do next is going to be very interesting. For the right now, let's at least fix this graph so that we can have a little more, it's a little bit spacious for me. Let's dumb it down. Fig dot update underscore layout, and we're going to have a height equal to 600, while we have a width equal to 800. Now that just shortens our graph. All right, next what we're going to want to do is we're going to get our non-linear regression line. Okay, non-linear. So first I'm gonna do have a little fun on my whiteboard real quick. So let's first put in our Anton equation. Since I don't really remember it real quick, let me go back to what it actually is. T-O-I-N-E, Anton equation. Well, thank you very much. That's all I have the room to work with. So, our Anton equation is log P equals A minus B over C plus T. What we want to do is we want to figure out how far apart each of these dots are going to be from our linear regression line, whether plus or minus. The way we figure that out is we're going to do something called a sum squared error. Our sum squared error gives us parameters for our nonlinear regression line to follow, so that we can take the errors that we get, plus or minus, and then the way we're going to put them all into one equation using sum squared is we're actually going to square it, and we're not going to use absolute value. Squaring it gives us a much better variable, and it allows everything to keep up and not to mess with how far off it was from the actual point. So how we're going to do that is we're going to put that right into our equation. Actually, let me do something real quick. Oops. So our sum squared error is going to be equal to log P minus A minus B over C plus T. We're going to square it all. Can we all see that? Perfect. And now how we implement that into our equation. So first let me talk about this. So our sum squared error is going to take all of our different variables, whether it be plus or minus, away from our linear, nonlinear regression line, and we're going to find one single answer. And what we're going to do is we're going to optimize that using our program. I'm going to show you how to do that using our program so that we can find exact parameters, so that we can graph a nonlinear regression line to see how far away each of our points are going to be already using making an average. All right, so let me just get started here. Put that away. So how we're going to start with this is we're going to put sum squared error is our variables, using our variables. Not variables, vector. Sorry, been a long day in math class. Using our vectors and our vector constants. They are A, B, and C, because log of P is our pressure, while T is our temperature. But A, B, and C are just constants. And they are going to equal V vars, V. And what we want to get out of this is a MP dot sum of our equations. And we're going to put in our log of, we're actually going to put that equation up there right into our code. Log of P minus, not capital, minus A minus, we want to do this correctly, all right? Or we'll get some hectic numbers. B divided by T plus C. So we have log, I did something wrong, I understand. We have log P, make sure that's what our, log P minus A minus B over, well, first off, that is actually C plus T. Doesn't matter, I just want to be correct though. Inside the variables. All right. Next, what we're going to do is we're going to use something called Skype. Skype is an optimization for root finding right here. And it helps with actually nonlinear and linear programming, which is what we are doing, so that we can find all of our errors. So what we want to do first is we want to import from Skype, S-C-I-P-Y dot optimize import minimize. So minimize is going to, we're going to minimize SSE, and then we're going to put in just random numbers for the moment, 10, 0 dot. All right. Now we only want the numbers down here, the array, because that is what it has gone through. We're going to hit a dot X, shift enter. Now we're actually going to find this as A underscore nonlinear, B underscore nonlinear, and C underscore nonlinear equals minimize. Minimize. That's easy. Oh. There we go. Let me show you that again, just so you see what actually happened. We have our array with random numbers, and now we're going to make our variables a, b, and c. Since we've already used a, b, and c in the equation up here, we're going to use a new a, b, and c called nonlinear. And what we want to do next is we are actually going to graph this new data that we have, and it's going to give us a non-linear regression model. So let's make another scatter plot. Short scatter, and x is going to equal t, while this time y equals a underscore nl minus b underscore nl divided by t plus c underscore nl. Nope. We want our mode to be lines this time, and our name is actually going to be the Anton equation underscore nonlinear regression of it. So it seems we did something wrong. Let me go back and fix it real quick. Let me see if I can find our error that we have. So x equals t, y equals a underscore nl minus bl plus t plus c. There may need to be parentheses in here. Oh. Now let's check back into this equation as well. Let's see, maybe our equation was wrong, and we can run it again. All right, so our equation was wrong. We do have that valid. And now our data is lining up as to it was before. But it looks like our Anton equation, our line is not exactly how it should be. So x equals t and y equals a minus b underscore a minus b over t plus c. You think it's our numbers in here? Let me see. correctly, see running time 1 divided by 0 and counted by double scalars. I'm just trying to figure out if it was just my computation that is wrong, or if there's actually a problem that we have within our code. Hopefully I can figure it out fast enough before our time runs out today. 1, 2, dot, comma. See something here. Our data was optimized. Our line is still down there. So what this could mean is that our parameters are just too far gone. It means they're no way in there, and our error that, like, I guess our starting vectors, they're just not right. They're too far out of what they should be. So there's a way we can fix this though. Excuse me. There's a way we can fix this. There's a method for this model. We're going to use linear regression now that enables us to find better starting parameters. All right, welcome back. So previously, we were trying to figure out why our Anton model for nonlinear regression gave us this line. But this happens when our data points aren't really, we have poor guessing. That's what, and it's not going to fit the model. Now, we can try better parameters or starting points, and we'll see if that fixes anything. But in the end, if we don't got it, we just don't got it. So what we can do next actually is there's another method, and that is linear regression. And how we're going to do that is we're actually going to use some math for this one. So just hold tight for 1 second. Let me make sure that everybody can see this. You can all see? All right. So what we're going to do is we're going to actually add on to this. So let's first erase the data. What we're going to do first is we're going to write out the Anton equation. Log P equals A minus B over T plus C. And now what we want to do here is we want to separate our X variable and Y variable and get our constants to the other side. So how we're going to do that is we're going to multiply everything by T plus C. So T plus C, T plus C, and even this T plus C. Now let me just clear that up. And what we're going to get is T plus C times log P equals T plus C times A minus B. All right, now what we can do next is we can distribute, and we can do T log P equals negative C log P plus A T plus A C minus AC minus B. And now what we can do, since these are all just one big constant, we can make this variable D. So now we have T log P equals negative C log P plus A times temperature plus D. Just cut that. Let me clear the board. What we have now is T log P equals negative C log P plus A T plus D. And since we have three vectors and two variables, we can use matrix multiplication and separate this out so that we can be able to implement our multiplication into our programming language. So let's start with our A sub t. We get T1, T2, T3, and Tn. And then we're going to have a negative log P, negative log P sub 2, negative log P sub 3, negative log P sub n. And then for our D variable, we're just going to be multiplying by a factor of 1, 1, 1, 1, 1. And there's our first matrix. It is a 3 by n matrix. What we can do next is we can multiply by A, C, and D, so we can get our final solution of T. Why didn't anyone tell me I was going to run out of room? Of T log P. T log P. But what we have right now is we're going to label these as X, V for our vectors, variable constants, whatever you want to name them, and they equal Y. This doesn't end, right? This doesn't end. It's right now it's a 3 by n matrix. So in order to help define it, we're going to need to turn it eventually into an identity matrix. The way we can do that first is do X transpose, which is basically multiplying it by itself. So X of t times X v is going to equal y X of t. And what we're going to do next is we're actually going to multiply it by the inverse of itself so that we can find our identity matrix. So we have X so t. Let me clear the page real quick. Give me 1 second. All right, let me clear the page real quick so we can restart fresh. Right now we have X transpose times X times our V constant equal Y to our X transpose. But we still don't have any parameters, and right now our function is endless. The way we're going to do that is we're going to multiply it by its inverse function. So it's a -1 equals yxt So this is what we have. We have X transpose times X to the inverse of itself times X transpose times X times V so that we can get our parameters and so that we can get our identity matrix is now going to give us a viable solution for our parameters. Now let me clear the whole page for you so I can write it out neat and simple. Sorry, just had to make sure I was doing it right. Xt times Xt x to the negative to -1. This is going to be our identity matrix, and these are going to be our parameters. So now we have a 3 by 3 times 3 by 3 times 3 by 1 equals 1 by n equals 1 by n times n by 3, giving us correct parameters. Still recording, perfect. So next what we are going to do is we are actually going to develop and put that matrix right into our code. The first thing we need to do is create our design matrix. Capital X now, since lowercase x was our independent variable. MP.c underscore t comma -log p comma mp dot 1 underscore like variable t, just so they're exact matching. Perfect. And now how to do matrix multiplication inside Python and Google Laboratory is we're going to use the @ sign, what we use for our emails. So x comma transpose t multiplied by x. Hey, you see what I'm talking about? You see what I'm talking about? Next, we're going to actually put that into our inverse so we can find our identity function, which is the math that I tried to explain. Sorry if you did not follow along. It's kind of hard to type today. mp.log.I inverse inv. Now we're going to multiply that by x transpose t. T at x, and now that is going to be multiplied by our other matrix x dot transpose, which is then going to be multiplied for our t capital T log times p, which is our y equals. Now we have some good parameters, like what we see here. I am liking what we're seeing here. So let's see if we can go plug these in real quick. 10, -34, and -2123. No, we cannot. Sorry. So what we're going to do next is we are going to have our linear regression. A underscore LR, comma, B underscore LR, comma C underscore LR. And that's going to equal NP dot LI and ALG dot inverse of our matrices, which is X transpose dot T at X, and then space times our next matrix, X dot T, capital T, and then for our next one, T times logs of P. T times logs of P. Perfect. And now A underscore LR, comma B underscore LR, comma C underscore LR will be our new parameters. There we have it. Now, what we need to do next is we need to actually plot again. So, it's going to be our last graph of the day. Fig.add underscore scatter. X is going to equal T. Y is going to equal A underscore LR minus B underscore LR divided by T plus C underscore LR. And actually this is B is no longer there. It's actually variable D. Let's go back to our it's actually variable D. Because if we remember, when we had B over C plus A, we lumped all of that into a D vector. So that's just keeping up with everything. But when we do our equation, it is still the same B underscore LR. Just want to make that noted. Mode is going to equal lines, and our name is going to equal Anton equation underscore linear regression. Well, looks like we are doing something wrong here. Give me 1 second so I can figure this out, okay? I don't know. Oh, I see our problem. We have x comma t, not x dot t. Let's restart and run all. it seems something is still going wrong. I am going to try to figure it out. In the meantime, let's make sure that all of our matrices are correctly being multiplied by each other. We have X transpose multiplied by matrix X, and then we have that multiplied by X transpose, and then we have multiplied by T log, and then that was going to give us, oh, I forgot to actually define my how do you, all right, I forgot to define my B underscore LR equals A underscore LR times C underscore LR minus D underscore LR. Says they're not defined because I did not define them. B underscore LR is equal to A underscore LR times C underscore LR minus D underscore LR. And that's how we code a linear regression line right there. All right. I'm happy. I hope you're happy for me. All right. Okay. That's how we do that. That is how we do that. Man, I was losing faith. Were you? I was losing faith just a little bit, but I think we'll be all right. So what we're going to do next is so today our non-linear regression line just wasn't in today, but our linear regression line was. So let's just restart and run all. Making mistakes builds character. But if you see our data is kind of following each point to the exact, what we're going to do is we're going to manipulate it a little bit so that there's a way to add a code. Add a code. There it is. Add another code so that T plot equals np.linspace. It's not how space. Linspace np.min of variable t and comma np.max of variable t comma is 100. Now that gives us that, and we're gonna go in everywhere there's a t and put t plot. Now we get a better, more gradual line. Thank you for your time. This has been linear and nonlinear regression on the Anton equation, measuring temperature in kelvins compared to water vapor pressure in pascals. My name has been Brandon Eugene, and I thank you for taking the time today.